Okay, so I'm going to go ahead and get started. Again, if you're still working on the lab, that's totally fine. If you have any questions with what you're doing in the lab, feel free to reach out to the support channel and our support team can help you get going with that. But now I want to talk about microservices. So this is one of the, I think this is probably the point in the lab where things start to kind of click and go aha, which is like, hey, why did we do all of this work getting this monolith deployed to Kubernetes? What are the real benefits of that? I think we're going to start seeing that with this microservices lab. So what we're going to cover is we're going to introduce something called the Strangler Pattern to help us take functionality away from a monolith and move it towards a microservice. We're going to learn about horizontal pod autoscalers, a Kubernetes resource that allows you to horizontally scale the number of pods that make up your deployment due to load. We're going to talk about how we can implement the Strangler pattern using Istio. And then we're going to take a look at how we can observe our service mesh within your namespace using a tool called KeyLoot. So let's go ahead and get started. So the Strangler pattern is a pattern that I don't know if it was coined by Martin Fowler, but he has a pretty good write-up about the idea behind the Strangler pattern by comparing this idea in practice to something that he observed called the Strangler fig tree. So I'm just going to read his quote here. One of the natural wonders of this area are the huge strangler vines. They seed in the upper branches of a fig tree and gradually work their way down the tree until they root in the soil. Over many years, they grow into fantastic and beautiful shapes, meanwhile strangling and killing the tree that was their host. So it's a pretty hardcore, right? You know, but it's something that I think really resembles a fantastic way to make sure that when we attempt to take functionality away from a monolith and move it towards a microservice, we can do it by imitating the Strangler fig tree here, right? So the idea is, you know, if you've got a huge monolith and you're slicing it up and grabbing individual pieces or components of your monolith and moving them somewhere else, eventually, if you've finished that and kind of followed that all the way through, there's going to be no need for the monolith that you originally started with. So here's how we can apply this pattern here. So the idea is we're going to add a proxy in front of the monolith. Initially, this first initial step, all this proxy is going to do is send traffic directly to the monolith. So this is actually a step that we've already done. The proxy that we've added in front of the monolith is that virtual service that Casey talked about in the previous lab. This proxy, all it does is send traffic directly to the monolith. It doesn't interfere with it in any way. It just sends it on forward. Next, we create a microservice from one single capability of the monolith. It's important to ensure that the microservice doesn't have any dependencies on the monolith. It needs to kind of function as its own self-contained unit. And then we'll configure that proxy that we have already established to route subsets of traffic to that new microservice. So we'll continue this process, these steps 1 and 2, over and over and over again until eventually the monolith is not serving any traffic anymore. And then we can just delete it, and now it's gone. So this is really nice because I'm sure that any of you who work in a large enterprise, there's got to be at least one application that no developer likes to touch, and it's disgusting, and it takes forever to deploy, and nobody feels confident in any of the changes that they make there. Well, when you use this pattern, you don't actually have to make any changes to the monolith. All you're doing is kind of cutting off traffic piece by piece until eventually you're left with a monolith that doesn't do anything at all. So let's take a look at how we can approach this. So recall that this is kind of what the reference architecture for SpringTrader looked like. So we've got our presentation layer, which is kind of served to us on the browser with HTML and CSS. We've got our REST services, which can communicates to our integration services using RabbitMQ, and then we've got our SQL database right here. So there's a unique opportunity here where we can kind of apply this Strangler pattern by inserting a line right here between the A and B here. So the way that we've able to figure this out is by looking at the network tab of our SpringTrader application. So if you're using a browser like Chrome or Firefox, you can open up your debugger tools and look in the network tab and refresh the page, and you'll see that there's calls to this market summary service here. So we're going to /SpringTrader or Spring NanoTrader services /API/market summary. And the reason we can tell that this is a good candidate for extracting some functionality out into a microservice is because these calls, these API calls, do not appear to be preceded by subsequent calls that would imply that this microservice has a dependency on the monolith itself, right? We want to make sure that we can find some self-contained functionality that we can extract without impacting the original monolith. So the way that we're going to do this is by copying some of the Java code from the monolith, in particular a controller called the market summary controller, and extracting it out into its own application that is deployed separately. So let's take a look at what some of this code might look like. So as we can see, we've got a Spring Trader market summary repository in the Liatrio GitHub organization. So we can see that right here. So there's a link to this at the top of this page here. I'll go ahead and post this in general if anybody is interested in following along. Market Git repo right there. So if you take a look at the master branch of this repo, already it looks significantly less intimidating than the Spring Trader application. So if we look at our build.gradle, there's a lot less dependencies. We only need the Spring plugins repo and Maven Central. We don't need the 7 repositories that we are currently referencing in Spring Trader's build.gradle file. We're able to use Spring Boot for this, so we don't have to use Spring MVC. We can kind of take this opportunity to modernize some of the software that we're using and switch to Spring Boot. All in all, the fact that this build.gradle can fit on one page is a massive improvement to what we've seen with Spring Trader. We can also see the market summary controller file and all of its dependencies from different files in the original Spring Trader monolith. All we have to do is copy those over and make sure that those don't depend on anything crucial within the monolith, so we can identify that slice of functionality that we can extract out into its own microservice. I'm not really going to go over a lot of this code here, but we do have something else to call out, which is that the market summary service is going to have its own self-contained database. It's going to be running an in-memory H2 database. You can see the import.sql file that kind of inserts some quotes into this database. This is only a subset of the file. I think there's like 50 of them in total. So we're going to be moving some of that data over into its own database. In a real production scenario, we would probably have a separate database that's running outside of the actual market summary application we're making, but this is kind of just for demonstration purposes. Let's take a look at some of the intricacies with our market summary deployment. So one of the differences that we're going to be doing here with our deployment is updating our liveliness probes and our readiness probes to take advantage of the actuators, the health actuators built into Spring Boot. Previously, our Spring Trader application was using probes that essentially brought you to the main login page of the Spring application. So by hitting that endpoint, you are actually receiving HTML as a response. But Spring Boot has its own health endpoints built into the actuator that you're able to customize in the application to allow this actuator to return different results depending on whether or not some of your dependencies are running or not. So that'll be a better way to customize whether or not our application is actually able to receive traffic. We can also notice that in the values YAML file for this new Helm chart we create, the resources that we specify are a lot slimmer than the Spring Trader app, right? So we're not using Spring MVC. We don't have a huge monolith. This microservice ultimately is only going to serve a JSON payload back to the monolith or back to the user to consume. And because of that, we don't need a huge amount of resources in order to do so, right? So here we only have about ½ a gig of memory and 128 millicores for our requests, and then around 3/4 of a gig of memory and half a virtual CPU. So a lot better. So let's talk about how Istio plays a part in this. So Casey kind of introduced Istio in the previous lab and talked about how it would be important for this lab and the future labs. And this is the reason why. What we're going to do in our new market summary microservice is we're going to create a brand new virtual service, just like we did for the previous lab. This virtual service is going to use the exact same gateway that the Spring Trader service used, and it's going to use the exact same host that the Spring Trader service used as well. The only difference is that we're going to have a route inside of our virtual service that matches this URI prefix, so /spring nanotrader services /API /market summary. right? That was the URI that we saw inside of the network debugging tools for when we visited SpringTrader. We're going to rewrite that path so that by the time the market summary microservice receives it, it's going to look like this. And all of the traffic that matches this condition is going to be sent to the market summary service instead. So in other words, if the monolith receives traffic that doesn't start with this prefix, it's going to send it back to the monolith instead of this new microservice. So we're configuring our proxy to intelligently grab all traffic that would have originally been destined for this controller and sending it to the microservice instead. And the beauty of this is we don't actually have to touch the monolith in order to do this. So it's pretty cool the way that it works. And when you configure virtual services like this, Istio is going to grab whatever happens to be the most specific match to whatever traffic it sees and send it to that destination. So we're going to see all of our traffic destined for here going to market summary. Anybody have any questions about this? Awesome. Let's talk about horizontal pod autos. Oh, sorry, go ahead.
Sorry, Parker. I was unmuting myself. So on the Istio configuration here, you're setting up the prefix by match, right?
Yeah, so previously our SpringTrader virtual service had a default route, so everything went to that, right? But now we only care about traffic that's matched this.
So theoretically, you don't need to route the traffic for the entire app there. You can do for bits and pieces.
Exactly.
Through this prefix here. Oh, I see. Okay.
Exactly. Yeah. Yeah, you've got it, right? So again, the beauty is we're only capturing a subset of that traffic that's meant for the market summary controller, and we're sending it off to our market summary service without touching the original monolith. So the nice thing is we can delete this virtual service, and it's not actually going to impact the end user. The user will just start sending their traffic to the monolith instead. They're not going to know what's happening behind the scenes. Does that make sense?
Yep.
Awesome. So let's talk about horizontal pod autoscaler. So a horizontal pod autoscaler is a controller deployed to a Kubernetes cluster that allows you, that essentially queries metrics that are specified in the specific HPA resource. We'll look at an example of what that looks like later. And it adjusts your replica count inside of a deployment or a stateful set or a replication controller to match a specific target to make sure that CPU utilization or requests per second are spread out evenly at a desired target amongst all of your replicas, right? So the reason why HPAs are useful here is because when you break a monolith apart into separate microservices, HPAs allow these microservices to scale independently of each other. So if we refer back to our monolith, if we have a very, very tiny piece of that monolith that is getting a ton of traffic, we have to scale that entire monolith up to X number of replicas. Whereas if that monolith was really re-implemented as a collection of microservices, we would only have to horizontally scale that specific service that was receiving traffic. So we can have 10 replicas for this really, really high demand service and 2 replicas for all of the other ones. So as you can see here, we've got our horizontal pod autoscaler. It makes changes to your deployment manifest, and those changes result in more pods in the result of a scale up or less pods when you want it to scale down. So we can take a look at some of the metrics that HPAs allow you to use here. So when you configure an HPA, you help it out by telling it what the minimum number of replicas you want it to use are, the maximum number of replicas, and what metrics you want it to use when scaling up or down. So in this case, we have a target average utilization for CPU of 80%. So the goal of this HPA now is to make sure that of every replica that you have running in this deployment, all of them should be roughly 80% CPU usage. And if it's seeing a number that's less than that, it knows to scale it down. And if it sees a number that's more than that, it knows to scale it up. We can use multiple resources here too. So we can also try to have a target average value of memory usage. Although in practice, I don't really see this metric being used as often for horizontally scaling pods. Typically, you see CPU a lot more, but you can do it for memory as well. You can also scale based on metrics from the pod in terms of the number of HTTP requests you receive per second. So in this case, we are trying to make sure that each replica in a deployment gets about an average of 100 requests per second. So again, if it's getting less than that, it knows to scale it down to a minimum. If it gets more than that, it knows to scale it up. Anybody have any questions about that?
So my question is this the ability to get more parts and reduce it, with the ability to configure this? Is this the feature of Kubernetes, or the underlying infrastructure service, AWS also gives this, right? So because
yeah. So if I understand what you're saying correctly, there's really, when you talk about horizontally scaling in Kubernetes, there's actually two concepts you have to be familiar with, right? So you want to use something like this to scale the number of replicas in your application, right? So that's, do you want one pod? Do you want two pods? Do you want three pods, right? But then there's another concept on top of that that's, well, what good are 3, 4, 5 pods if I don't actually have nodes in my clusters support that? Right. So when you think about it from that perspective, then sometimes you'll have to lean on a cloud provider's ability to automatically scale your Kubernetes worker groups to make sure that there's the correct number of nodes for your applications to run on. Does that kind of make sense? In our case, we use a deployment called Cluster Autoscaler. So we actually deploy that to our cluster, and then Cluster Autoscaler essentially monitors the scheduler and says, hey, if my pod that I'm trying to schedule has no room, like the scheduler doesn't know where to put it because there's no room, the Cluster Autoscaler knows to scale our ASGs for our EC2 instances up by 1. So that way we now have a new node that our pods can run on. And the Cluster Autoscaler also implements a loop that makes sure that when we have nodes that aren't being utilized as much, to scale those down. I know that Google Cloud has its own way of doing that as well through GKE. I'm not sure how it's done on Azure, but I think you can use Cluster Autoscaler for any of those as well. Is that kind of what you're asking? Awesome. All right, let's take a look at Kiali. So Istio is a great tool to deploy to your cluster for giving you a service mesh, probably only because Kiali exists. I would say that the fact that Kiali exists is Istio's best feature by far. And it really is amazing, the ability that you have to observe your cluster through something like Kiali. So for any of you who have deployed your application in Lab 2, you can actually run Sparky Links in your Slack workspace, and you will see a link to Kiali, and you can poke around there when you want to. But the idea behind Kiali is to kind of complement Istio in the sense that you can use it to build a graph of all of your applications that are running there, and all of the dependencies of your applications, and tracking metrics like the amount of requests per second your app gets, the number of replicas that it has, etc. So it's a great observability tool that only works in Istio-enabled clusters. So when you open up Kiali for the first time, you're presented with a list of namespaces. Probably what you'll want to do when you open it is take a look at your namespace. So it's going to be the name of your Slack channel - staging. You can click on this button to open the graph. From the graph, you can take a look at the edge labels and look at requests per second. And then from there, you should be able to see kind of like a GIF, I guess. I'm not sure what the word I'm looking for, to visualize what the traffic is looking like when it hits your Spring Trader application. I think you have to enable this traffic animation thing too. Does the next slide show it? Kind of does. I'm gonna pull it up on my screen. I think it's better. I'm gonna do Sparky Links. Go to Kiali. So when I go to Kiali for the first time, I'm gonna go to Graph here. I see Parker Lab staging. So on my edge labels, I've got requests per second, as well as a display for a traffic animation. I'm turning that on. So now we can see that from the outside, we are actually receiving 18.71 requests per second to my Spring Trader application. You might be thinking, wow, it's a really popular application for something that was just deployed an hour ago. We actually have a program running inside of our Kubernetes cluster that is generating traffic against all of your Spring Trader applications and eventually all of your microservices that you deploy at the end of Lab 3. So it's going ahead and sending traffic out to the public internet and then into this Istio Ingress gateway so that you can see it in Kiali. This is only going to show you anything if there's actually traffic hitting your SpringTritter app. So if I turned that traffic generator off, you wouldn't really see anything here. So we went ahead and added that to make it easy to see what was going on inside of your namespace. How's that sound? Does that make sense, everybody? Anybody have any questions? Awesome. So with that, we are now going to get into Lab 3, probably my favorite lab, because what we get to do here is work on cloning the market summary application from GitHub, trying to get it deployed with Sparky the same way that you did with the SpringTritter application, and using a virtual service to strangle that specific piece of the monolith and move it over to this microservice. And then by the time you're done, you'll be able to take a look at Kiali and see that now you have two applications that are both receiving traffic. And the best part is that your main SpringTritter application will still work afterwards because all we did was strangle that functionality from one service to the other. I'm going to go ahead and let you guys loose. Again, feel free to ask on Zoom or ask on the support channel in Slack if you have any questions, comments, or concerns.